Forgot my pen. Right, so this is our worked example of a Born-Haber cycle here. We've got a bunch of data given to us in the question as usual, and the task is to calculate the lattice dissociation enthalpy for sodium oxide Na2O. So I've got my framework for my Born-Haber cycle here. First step is always to put the solid lattice, the compound, on the bottom line. So in this case that's sodium oxide, Na2O solid, that goes there. And then the first enthalpy change we're going to put in is formation. So we're forming sodium oxide from the elements, that's this change here, delta HF. And we're forming, what are we forming from? Well, we're forming from the elements, so that's sodium solid and oxygen gas. We need 2 sodiums and 1 oxygen atom, so half an oxygen molecule. Okay, now we have to start going around the loop. So the first thing I'm going to do is atomize my sodium here. And of course remembering that because it's 2 atoms of sodium, I'm going to need to times that by 2. So that'll make my sodium gas. Now I'm going to atomize the oxygen. Remember, enthalpy of atomization is the energy change to make 1 mole of gaseous atoms. So because I'm making 1 mole of gaseous oxygen atoms, I just need 1 atomization of oxygen there. Okay, let's do some ionization. We'll ionize sodium first. So we're going to ionization energy of sodium, and again because we're making 2 sodium ions, that will need to be times by 2. That'll release 2 electrons even, and then we'll need our oxygen gaseous atoms. Okay, so far so good. Now we have to start putting electrons into oxygen. Of course, oxygen forms the O2 minus ion. That means we can do this in 2 stages now. So the first stage, I'm going to add the first electron. That's always exothermic, EA1. So that's made, we've now got 2 Na pluses, gaseous state, 1 electron and O minus. And then we're going to put in the second electron. Now the wide awake amongst you will notice that the second electron affinity for oxygen is endothermic. In other words, we have to put energy in. That's because we've got a negatively charged ion and we're forcing a negatively charged electron into it. There's a bit of repulsion there, so we get an endothermic process. We have to use a bit of energy to get our electron in. Okay, so we've now got 2 sodium ions and we've got 1 O2 minus ion there. Okay. That only leaves the lattice dissociation enthalpy. Now, dissociation, the opposite of formation. If we're dissociating a lattice, we're taking the lattice and we're breaking it into gaseous ions. So the dissociation enthalpy is there. Delta H lat dis, sodium oxide. Okay, well let's put in some numbers. So delta HF for, that is minus 414. Then we need 2 lots of atomization. We need 1 lot of atomization for sodium, for oxygen, 2 for sodium, 1 for oxygen. We need 2 lots of 5O2. I'll try and write the number rather than the formula for sulfur dioxide this time. EA1 there is minus 141, EA2 is plus 798. Okay, there's a lot of information on here. If you were drawing this in an exam situation, you wouldn't necessarily need to write all the stuff that I've written here, all the separate dissociations, because, well, it depends what the exam's asking for, of course. Okay, just needed my cheat sheet there. So we're trying to work out our lattice dissociation enthalpy there. Lattice dissociation enthalpy. So using Hess's rule, enthalpy change is independent of the route taken. If I want to go from here to here, then the energy taken by this route is the same by this route. So let's follow the other route. So for starting off that delta HF there and going in the opposite direction to the arrow, change the sign. Then I just need, well, let's just do these on the fly. So 2 lots of 107, 214, then a 249, 2 lots of 502, and take away, we're going in the same direction of the arrow there, minus 141, and then the same direction of the arrow there, plus 798. What does that come to? 2538. That's the lattice dissociation enthalpy there. If I wanted the lattice formation enthalpy, what would that be? Well, that would be the exact opposite. There's our lattice formation there. Lattice formation and lattice dissociation are the exact opposite of each other. So if I was asked for the lattice formation, it would just be minus 2538. Okie dokie.